Today we're going to talk about rate of change, and we're going to think back to that first day where we talked about what calculus is about and how we study calculus with two major questions. What is the slope of the line tangent to a function at a point? And the other question was, what is the area under a curve and above an interval? So we want to focus on that first question. Recall that this is one of the big questions that we have in calculus. What is the slope of a line tangent to a curve at a point? To make our lives easier, we're going to start by describing the curve with a function. When we talk about a line tangent to the curve, we imagine a line just kind of skimming across the function. So here is a line tangent to the curve. So when we talk about a tangent, this is the same tangent that we had back in the days of geometry where we drew a line tangent to a circle. It's just tangent to a more general type of curve. That's a tangent line to a curve, and this is at a particular point. The question that we're interested in is, what is the slope of this tangent line? What is the slope of this line tangent to a curve at a point? Notice if I pick a different point on this curve, if I pick a different point on this curve, I will get a different tangent line. So this tangent line business is local to a point. So if I pick this point back here, that's a tangent line at A. So we're going to say that this is the tangent line at x equals c. So we'll be specific about which tangent line we're talking about. What is the slope of the line tangent to a curve at a point? So think visually of what's going on. The tangent line just skims across the surface. What we want to think of as in terms of the tangent line is that the tangent line represents the direction that the curve is going at that moment. Which direction is the curve going at that moment? We can think of this slope as the direction of the curve at that point. We're going to think of this slope as the direction of the curve. Now this keeps changing. Down here at this point A, our direction is generally this down and to the right. And then later on, our direction is up. But we're thinking of the slope of the tangent line is describing the direction at that point. Imagine that this is train tracks and the point is where the train leaves the tracks. Where does it go? So if we're cruising along here on our roller coaster and our roller coaster lets go at this point C, the track's no longer making us curve and we just go in a straight line away. It's a roller coaster in space, so there's no gravity to worry about. There is atmosphere to worry about, so I hope we bought some bottles of air. But that's the direction it would go. Imagine if you had a tennis ball on a string and you were spinning it around. I have to mimic this. I can't actually have one because I have a dog. And so if I'm practicing in the house, the dog's like, oh, heck yes. And then he like jumps for the ball and like crashes through the TV. It's like a whole thing. So, but if we're spinning a tennis ball around, the tangent is where the ball is going to go when I let go of the string. Here's our tangent, our ball spinning around in a circle. And if we let go at this point, the tangent is where the tangent is the direction that things are going to go. You watch Thor in an Avengers movie, and you try that as a kid, and you end up getting hurt. You just figure you need a bigger hammer. And then you like jump, and then hit yourself with a hammer. Maybe I'm just unfortunate. So think of the tangent line as the direction things are headed. That's what we care about. Slope indicates a direction. And so the slope of the tangent line is the direction that the curve is going. At that point, in terms of rates of change, we're going to imagine this as the instantaneous rate of change at that point. It's a speedometer reading. When you're driving down the freeway, your speedometer said, what's the speed limit? On like 280. Is it 65 or it's 70? 70? It should be 80, but because it's not really 70, because speed limits are bullshit. Because I've been passed, if I'm going 70, you're going to get passed by the police who are sensibly like, oh, that's too fast. Get out of my way. Anyway, that's all beside the point. So you're driving down 280 at a nice, reasonable 70 miles per hour, because that's legal. Your speedometer is telling you the slope of the tangent line of your position at that moment. At that instant. You haven't actually gone anywhere. But at that point, you're going 70 miles per hour. Any questions? Let's pick a function and let's try to figure out what this would be. Oh. So we're going to use our favorite, the instantaneous rate of change or instantaneous speed. How fast are you going at that moment? Let's talk about this. Let's talk about slope. How do we calculate slope? Thank you. How do we calculate slope? Slope is rise over run. What's a slope formula? Sometimes we're comfortable with formulas. What's a slope formula? How do we calculate slope? You may have seen the slope described as the change in y divided by change in x, the rise over the run. How much the vertical changes divided by how much the horizontal changes. How much vertical change we get per unit of horizontal change. Sometimes we abbreviate change with a capital delta, so delta y over delta x. What is delta y? How do we calculate delta y? It's the one with minus, for those of you who don't want to say anything. I understand. You didn't want to say anything because, man, what if I'm wrong? I know that if I'm wrong, then Leach will throw the coffee cup at my head, which is very... I'm just kidding. I would not throw my coffee cup. It has coffee in it. That's why I can't have stuff on the desk that I can throw easily. That's why I've had to have like this. I go, what? You got the slope formula wrong? Ah, this is too heavy to throw, and I'm balanced. That's why I've wired all the chairs with electrodes, and I just have to push a button in. I'm just kidding. That's why I don't teach high school anymore. It's like, well, you know what I need? I need like a shock collar, but for all the seats in the room. I'm like, oh, Leach, that's inhumane. But I was teaching at a Catholic school, they're like, so I go, Leach, that's inhumane. We love it. Okay. So I knew I had to get out. I'm like, oh no, this might be a bad match. So y2 minus y1 over x2 minus x1. That's how we calculate this. We have 2 points. We have 2 points. We got a point down here. This is going to be x1, y1, and some point up here. Call x2, y2. I want the slope of the line connecting them. I've got my run, and I've got my rise, a little right triangle. We just find the difference in the y values. That's how much the y's went up. And then divide that by the difference in the x values. That's how much the x's went to the right. This is our favorite. This is the default mode of tracking change. We make linear functions all the time. We just take whatever's happening now and say, that's what'll happen. What's the problem with this plan applied to the problem at hand? Why is this going to be a problem when I want to find the equation of the slope of the tangent line at a point? What's the problem? We only got 1 point. What happens if we only have 1 point? What's y2 minus y1 with just 1 point? 0. And what's x? That's not a problem, right? It's just no change. We can have no change. But what's x2 minus x1? Also 0. That's the problem. Now I've got 0 over 0. What's 0 divided by 0? We like to say undefined, right? It's actually not undefined. 0 divided by 0 is what we call indeterminate. That's my math teacher actually moment. It's a completely irrelevant difference for our purposes. 0 divided by 0 is in the category of no. Right? That's the problem. If we've only got 1 point, this is going to be 0 over 0. I'm going to write it in red because it's an emergency. If we've only got 1 point, but if there's only 1 point, then m is equal to 0 over 0. If it's something else divided by 0, like 1 divided by 0, that's undefined. But 0 over 0 is called indeterminate. Because it might be 1. It might be 0. It might be infinite. And it might be anything other than 1. So when you're like, oh, what's 0 divided by 0? You can actually just be like, oh, well, what do you want it to be? Okay, so the problem is if there's only one point, which is the problem that we want trying to solve, we end up with 0 over 0. So we're going to have to approximate it. There are 3 great tricks in mathematics. There are 3 things that, for the most part, these are the things that you do to deal with problems in math. The 3 things that you do in math: add 0, multiply by 1, do an easier problem, drop it back to an easier problem. So what we're going to do to deal with this, I can't have this 1 point, 0 over 0, no good. We're going to get 2 points, and we're just going to make them close together. So we're going to approximate the tangent line with a secant line using 2 points that are close together. That's our workaround. We're going to approximate the tangent line with a secant line. Secant line just means we're going to pick 2 points and draw the line connecting those. Because if I have 2 distinct points, I can use the slope formula. I can do y2 minus y1, that's not the problem, but I can do divide by x minus x1, or x2 minus x1. I can make that happen. So I'm picking a second point. So our strategy is choose a second point that's nearby. And then make an approximation of the tangent line. We don't just pick some rando point. We pick something nearby on the function. Questions? Doesn't seem like much. This seems like a natural thing that we would do, but there's a lot going on. Number one, we want to recognize what we're trying to do. Find the slope of the line tangent to a curve at a given point. We want to recognize the tool that we want to use for this, slope formula. We want to recognize the problem that that tool has. Needs 2 points, have 1 point. So our solution is to make the problem fit the tool that we have. pick a point that's nearby, because notice that the slope of this secant line is pretty close to that of the tangent line, although not very good. How can I improve my approximation? Do what? Choose a closer point. So this is going to make an approximation to our tangent line that we can improve by choosing a closer point. So that we'll still have 2, but we're making our delta x smaller and smaller and smaller. We're going to improve our approximation by choosing a closer point. The next step is the calculus thinking part. The next step is to keep doing this forever. That is, think about what happens as I move that point closer to the point we care about. What happens as this difference gets closer to 0? We know we can't make it 0. We can't just plug in 0, because then we have 0 over 0, indeterminate. We've got to think about what happens as the gap between the points gets closer to 0. That's the calculus thinking. What happens if we do this forever? That's the calculus thinking. We'll just keep doing this and think about what happens. The lights go out. We break the power grid. You're trying to divide by 0. I'm getting very close to dividing by 0, but not actually dividing by 0. How close do we get? Infinitely close. What does infinitely close mean? Welcome to the weird part of calculus. That's the weird part of calculus. That's where we get to the point where infinity is weird. What happens if we do this forever? What happens as those points get arbitrarily close together? What's happening to the slope of that secant line? The closer I make those 2 points, the closer my secant line is to my tangent line. The tangent line is what happens when those points are exactly the same, but we can't do that. That gives us a 0 divided by 0. Any questions? Is everybody okay? Is weird W-E-I or W-I-E? That looks like it's spelled wrong to me. But if I wrote it the other way, that also looks wrong, which I think is entirely appropriate for a word like weird. Yeah. Any questions? How's everybody okay? This is a brief history of time-style calculus. Notice I didn't write down any kind of formulas for anything. Just wanted to establish the thinking that we're going to be using when we think about this question. Identify the tool that we have. It's the same tool that we had before for slope. Changing y divided by changing x. The problem is changing y was 0, changing x is 0 because we only had 1 point. So we solve just like an engineer would solve. Well, let's pick a point that's closer. That's close. And you're like, oh, how close? It's like, oh, how close can you get it? Can you make it smaller? Yep. Yep. And we can, just happens to be that mathematically, we can do that forever. We can make the points infinitely close together. How's everybody okay? Of course, because none of this looks like a problem that you would encounter on a quiz or a test or something like that. You're like, oh, this is just blah, blah, blah. This is not due problem on tests. So of course we're okay. But I'm like, yeah, no question. This is like when you assign reading for homework. There's no homework. This is because I don't want you to have to do anything. I want this running in the background. You know what I'm going to be talking about tomorrow? The same stuff. It's going to happen only faster because you don't get a song stuck in your head by hearing it once. You get your song stuck in your head because you hear someone say it, sing it, play it on the radio over and over and over again. So I say the same thing for like the next 17 weeks. So this kind of thinking gets stuck in your mind and you can't get it out of your head. I don't want you to memorize stuff. I just want you to remember it. Any questions? Comment? Snide remark? All right, that's going to do it for today. Thinking about rates of change. Think about slope of tangent line, approximating it with secant line, and make those points closer and closer together. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.